Hello and welcome to the final lesson of Chapter 3, 3-4. We're going to be dealing more with exponential and logarithmic equations. Solving some simple equations. I've given you some examples here. So if I have 2 to the x equals 32, each of these are similar to examples we've had during our chapter so far. So I would know that I would be saying 2 to what power equals 32, which I could rewrite it both in base of 2 to get a solution of x equals 5. That would be a 1-to-1 property. Natural log of x minus the natural log of 3 equals 0. I could add the natural log of 3 to both sides. I have a 1-to-1 property, x equals 3. 1/3 to the x power equals 9. I can rewrite it as 3 to the negative x power equals 3 to the second power. Drop the bases, x equals -2. Inverse function, the natural or e to the x power equals 7. If I take the natural log of both sides, then it causes the e to the x to go away to just become x. So I get x equals the natural log of 7. Likewise, I have the natural log of x equals -3. Basically, make both sides an exponent to base e. So e to the ln of x equals e to the -3rd, and so my answer is e to the -3rd. The log of x equals -1. Well, if I raise both by base of 10, then I just simply get 10 to the -1st power, which is 1/10. Log base 3 of x equals 4. Basically raise both sides to the 3rd power, and I get x equals 81. Another way you could do it is 3 to the 4th power equals what? And that would be 81. So those are examples of 1-to-1 and inverse properties applied to exponential and logarithmic equations. Notice how they interact with each other. If you have an exponential equation, chances are you're going to use a logarithm to solve it. If you have a logarithmic problem, you're going to use an exponential to solve it. They kind of interchange with each other. So some strategies for solving exponential and logarithmic equations. Number 1, rewrite them in a form that allows the use of 1-to-1 properties. Rewrite an exponential equation in the logarithmic form and apply the inverse property. And likewise, if you have rewrite a logarithmic equation in exponential form and apply the inverse property. If I have 3 to the x equals 4, I could take the natural log of both sides. If I have log of 3 equals 4, I could raise both sides by the base of the logarithm. And those would be applications of the inverse property. So in this case, solve each equation and approximate the result to 3 decimal places if necessary. Let's go with A. I've got e to the -x squared equals e to the -3x minus 4. Well, if I take the natural log of both sides, basically because of the inverse property, boom, I drop it. I could also call it a 1-to-1 property, that they have the same base, and drop it. So I get -x squared equals -3x minus 4. If I add x squared to both sides, I now basically have a problem that is a quadratic from Algebra 1. And I'm going to ask myself, what times what equals 4 that subtracts to be 3? And I would get x minus 4 times x plus 1. Therefore, x equals 4 and x equals -1. On the next one, I have 3 times 2 to the x power equals 42. I would divide both sides by 3 to get 2 to the x power equals 14. Now, it is apparently obvious to us, at least it should be, hopefully, that there is simply no easy way that 2 becomes 14. So what I'm going to do in this case is I'm going to take the natural log of both sides. By doing that, I can roll the x off and rewrite it as x times the natural log of 2 equals the natural log of 14. Divide both sides by the natural log of 2, and x equals the natural log of 14 divided by the natural log of 2, which, let's punch it into a calculator. I'll take natural log of 14, and I will divide it by natural log of 2, and I get 3.807. Okay, so once again, I isolated the exponential. Then, because it was an exponential form, I took the log of, or the natural log of both sides. I could have also done just log of both sides. I would have gotten the same answer. From there, because I took the log of both sides, the inverse property, the inverse property applied, and it got rid of that for me, and I was good to go. Solving an exponential equation. So I have 2 times quantity, 3 raised to the 2t minus 5 power, minus 4 equals 11. Okay? So I'm going to treat the 3 to the 2t minus 5 power like it's a variable, because I've got to isolate it first before I can do anything with it. I'm going to add 4 to both sides. Then I'll get 2 times 3 to the 2t minus 5 power equals 15. Divide by 2, 3 to the 3t minus 5 power equals 7.5. Now obviously there is no simple power that we can think of in our head. So let's go ahead and take the natural log of both sides. I'm now going to roll off my log. 3t, or 2t minus 5, times the natural log of 3 equals the natural log of 7.5. I'm going to divide by the natural log of 3. So I'll get the natural log of 7.5 divided by the natural log of 3. So I'll have 2t minus 5 equals 1.83. I'll add 5 to both sides. Let's rewrite it over here. 2t equals 6.83. Divide by 2, 3.4, and I would have 1.5. Solving exponential equations of the quadratic type. Solving logarithmic equations. So what I'm going to do in this case is I have a logarithmic. Now I'm going to use exponential for it. So I'm going to say the natural log of x equals 2. So now what I'm going to do is I'm going to make both sides of it the exponent for a base e. Because when I do that, now all of this goes away, so I have x equals e squared. So now I'm going to take e to the second power, and x equals, we'll call it 7.4. So once again, I raised each side by an exponent. Basically, I've made each side the exponent to the same base that the natural log has for its logarithmic function, because it's naturally a log base e of x. And by doing so, the natural log and e are eliminated, and I know e is a number, so I just e to the second power. plug it into the calculator. On the next one, I have a 1-to-1 example. Because they're log base 3 and log base 3, I can drop these and just solve. 5x minus 1 equals x plus 7. Subtract x, add 1, 4x equals 8, divide by 4 and x equals 2. Now in this one, I need to do some trickery first. I'm going to recall the quotient rule from the last lesson, 3-3, stated that if I had the log with a base and two things were being divided in the argument, then I could separate them out by subtraction. So now what I'm going to do is I'm going to reverse that. So I have log base 6 of 3x plus 14 over 5 equals log base 6 of 2x. Well now I have log base 6 equals log base 6. They simply go, the logs, they roll along. So now I get 3x plus 14 over 5, why did I write 15? Equals 2x. Multiply both sides by 5, and I get 3x plus 14 equals 10x. Subtract 3x, 14 equals 7x, divide by 7, and x equals 2. So once again, I used the quotient property to take the subtracted statements and put them in a divided form. Once I did that, I had the same log on the left as I did on the right, so I was able to drop them by the 1-to-1 property and then just simply solve like basic algebra. Solve 5 plus 2 times the natural log of x equals 4 and approximate the result to 3 decimal places. So I have 5 plus 2 times the natural log of x equals 4. I'm going to subtract 5. So I'll get 2 times the natural log of x equals negative 1. I'm going to divide by 2. So I get the natural log of x equals negative 1/2. I need to get rid of the natural log. That's the only thing hanging me up. So what I'm going to do is I'm going to raise them both by e, meaning that I'm going to put left and right of the equal sign as the exponents for the number e, because the natural log naturally has a base of e. So now I get x equals e to the negative 1/2 power, and I go to my calculator and I type in e to the negative 1/2 power, and I get 0.607. Solve 2 times log base 5 of 3x equals 4. First thing I'm going to do, write it out here, divide by 2, log base 5 of 3x equals 2. I'm going to raise both sides by the 5th power. Why? Because I've got log base 5. So now I get 3x equals 5 squared. And I'm going to divide by 3. So x will equal 25 over 3, which is 8.33. Now you might have asked, well, why didn't you do the squared first and then divide? You could do that, certainly. Checking for extraneous solutions. Solve log base 5, or log 5x equals log of x minus 1 equals 2. So what I'm going to do in this case, I'm going to solve it. I'm going to do a product here. Log, and I'll get 5x times x minus 1, and all that equals 2. I've got a base 10 here, so I'm going to raise both sides by the power of 10. So now I'll have 5x times x minus 1 equals 100. So now I'm going to multiply that through. I'll get 5x squared minus 5x equals 100. I'm going to subtract 100 from both sides because I've got a quadratic. So I'll get 5x squared minus 5x minus 100 equals 0. Now to solve this, I have to factor it. Let's factor out a 5 first to make this easier because they all have that in common. So let's write it up here. 5 times x squared minus x minus 20. Now it becomes a more simple matter of, shall we say, plugging it in, or reverse plugging it in. I ask myself, what times what? I have a negative 20, so I need a positive and a negative that will multiply to be 20, but because I have a negative x, I need them to subtract to be negative 1. Well, I know that I will have x minus 5, x plus 4. The reason why, if I were to draw it a t-chart, I could have 1 and 20, I could have 2 and 10, and 4 and 5. The negative tells me they need to be different, so that means they are going to subtract to be negative 1. So whichever one of these has a combination of difference that would be negative 1, which 4 and 5 do, is my solution. And since I need the negative to be larger, I put that with 5. So now I've got x equals 5 and x equals negative 4. Now I'm not done yet. The example said we were checking for extraneous solutions. And that is, we have to verify that this will be correct. Now you will recall from when we first talked about logarithms that we had a very, very important statement, and that was that you cannot have the log of a negative number. It's the only time that you're going to get an undefined solution. Why? Because when we look at the graph of it, the graph of a logarithmic function at its very core goes like this. That's the graph of a logarithmic function. It has a vertical asymptote at x equals 0. Meaning that unless I have some transformation, which I don't have here, I can never have a log of a negative number because it is simply outside of the domain of the function. It is restricted. So as a result, I can immediately say this one is an error, because if I plug it back in there, I'm going to get the log of negative 20 plus the log of negative 5. And that's going to be error. That will not work. So therefore I can state that really x equals 5 is the only solution. So it's always helpful whenever I get a solution or I get multiple solutions, especially when I get multiple, plug them in to make sure that they do not give you a negative number as the argument of the log, because otherwise you're going to be wrong because you haven't checked for an extraneous solution. Because while algebraically at first it may solve to be that potentially because of the quadratic, in reality that doesn't work. Okay? And that concludes our final lesson for this chapter.